All right, so for projectile motion, a projectile is considered to be any object traveling within the Earth's gravitational area of influence that is unpowered. Okay? It is in unpowered flight within the grasp of Earth's gravity. Okay? So, the simplest projectile is a falling object. If I drop something, it is by definition a projectile. It is in unpowered flight. Okay? Now, I know you're probably saying, but it's not flying, it's falling. But what is flying other than falling with style? If you've not seen Toy Story, you're missing that one. Like you're missing a lot by not seeing Toy Story. Right? But it's true. Anything that's moving through the Earth's gravitational field unpowered is technically flying. It's also technically falling. Okay? It is both. For example, the International Space Station is a projectile. It is in unpowered flight within the Earth's gravitational field of influence. Okay? It is also falling all the time. They're probably going, Coderre, you're so full of crap. If the International Space Station was always falling, it would burn up in the atmosphere. Nope, it wouldn't. In order to make something orbit the Earth, you just have to make it go fast enough that the distance it falls is equal to the distance the Earth curves away. It's a projectile. It's always falling. That's why people on it feel weightless. Okay? I mean, you've probably seen those videos. I'm going to show you a whole bunch in the circular motion unit of Chris Hadfield and zero gravity. Okay? On the International Space Station, they're only experiencing apparent weightlessness. They still have weight. They're still attracted to the Earth. Okay? That's why they don't fly off into space. So they actually still have weight. They're just apparently weightless. The same thing can be produced if you get into NASA's Vomit Comet. Their zero gravity training plane that just flies like this and makes apparent weightlessness. That's how they train for it. Okay? So any projectile, I mean, think about this. If you're falling, you jump off the diving board at the pool. Okay? Do you feel weightless while you're falling? You do, because there's nothing to tell you you have any weight. Nothing's pushing on you. The only reason you feel like you have weight is because you feel the Earth pushing back. Okay? Right now, I feel my weight in my feet. Earth is pulling me down, okay? And I push on the Earth, and the Earth pushes back, and I feel my weight. Same thing is happening to you sitting in your desk. Okay? Earth's gravity is pulling you down into the seat of your desk, and the desk is pushing back up on you. That's the force you feel. Okay? You don't actually feel your weight. You feel your apparent weight. That's why sometimes in an elevator, you feel heavier, and sometimes in an elevator you feel lighter. Depends how hard the floor is pushing on you. Okay? So, anything in unpowered flight is a projectile. Okay? Simplest projectile is a falling object. Okay, now, projectile motion has at least, well, can have two dimensions. If I just drop something, its motion only has one dimension. It's falling straight down. Okay? But if something is thrown, its motion has a horizontal component and a vertical component. Okay? The vertical component is accelerated motion because gravity is what's going to bring it down to Earth. Okay? The horizontal part is actually a constant velocity because there's nothing to slow it down horizontally. Okay? So any object that you throw, okay, is going to move horizontally at a constant velocity and accelerate vertically. What shape does a thrown object always show? Okay, see a bunch of people doing this. Okay? Any thrown object is going to make an arc. Okay? When you were a kid playing, with a water gun or the hose in the backyard, and if you wanted to get your little brother wet, okay, you'd aim the hose at him, he'd run away, so you'd tilt it up a little further so the water would go further, but it always made an arc. Okay? When you did that. Right? Because every single water droplet in that stream of water is a projectile. Right? They're moving horizontally and vertically at the same time. Okay. All right. So what goes up must come down. Okay. That's what makes a projectile have that arc. Okay. If I throw something up in the air, okay, it has to come back down. Right? Gravity is going to return it. The two halves of that motion are going to look very similar because the speed horizontally is not going to change and the acceleration vertically isn't going to change. Okay? That's why we get those arcs that we're familiar with. Okay? They're very symmetrical shapes. Okay, let's talk about something practical here. Let's say I'm doing archery. Right? I want to hit a target that's on that wall. Do I aim for the bullseye? If I want to hit the bullseye, I better not. Where should I aim? Just above it. Because in the time it takes the arrow to travel across the room, gravity is going to pull it downwards. Okay? That's that arc we were talking about. Okay? So if I aim at the bullseye, I'm going to end up under the bullseye because gravity will pull the object down. It'll drop across the room. Okay? This is something that any archer, marksman of any type, okay, even a quarterback, has to take into account. Okay? You never see a quarterback throw a ball on a rope. Okay? It's never straight. Okay? It's always going to be a little bit of an arc. Okay? Faster the object goes, the less you notice that arc, okay? Because it travels so fast. Okay? But that arc is always going to be there. Okay? Way back start of the unit, we talked about the longest sniper shots. Okay? We talked about how complex a shot like that has to be. Okay? And that's because that bullet is a projectile. And as soon as it leaves the barrel of the gun, gravity is acting on it and pulling it down. Okay, let me ask you this. Which of these hits the ground first? The bullet fired from the rifle, or a bullet held next to the rifle and dropped at the same time the trigger is pulled? Which one hits the ground first? Both at the same time. They're not going to hit the ground in the same place, but they're going to hit the ground at the same time. Okay? Because they both are going to fall the same distance. Okay? If I hold one bullet right next to the rifle and I pull the trigger on the rifle and drop the bullet at the same time, they fall the same distance. Gravity affects them equally. Okay? Sure, the bullet is going to hit the ground way over there somewhere, but it's going to hit the ground at exactly the same time as the dropped bullet. Okay? Because they're each affected by gravity in the same way. Okay? It's strange, but it's true. Okay? All right, I'm going to show you a quick video, and I want you to just, first time you watch, just watch it. Be impressed by the amazing thing that they do in this commercial. Okay? Then when we watch it again, I want you to think about it critically. Okay? And see if you can pick out any problems with it. Is it just trick photography? Like, is there a way for that car on the ground to win that race, like it showed in the picture, or in the video? There is. The car on the ground should win every single time, based on the way they set that up. What advantage, significant advantage, was given to the car on the ground?
The car started before they dropped it.
Right. That car was already in motion. In fact, it was traveling at its top speed. Okay? So along the ground, the car on the ground is underpowered. And it's traveling in its most aerodynamic dimension. Did you notice when they dropped the car from the helicopter that it fell flat? Cars don't do that. If you drop a car from a helicopter, it's going to nose down. Okay? And it's going to fall in its most aerodynamic dimension. But in the real world, all falling objects eventually hit what? Not the ground. Because they do eventually hit the ground too. What do they hit?
Terminal velocity.
Their terminal velocity. Okay? Objects falling through the Earth's atmosphere can only go so fast. okay, before the force of friction or air resistance is balanced by the force of gravity. Once that balance happens, they stop accelerating, and they fall at a constant velocity, the terminal velocity, the rest of the way to the ground. Now, terminal velocity sounds scary, and it's fairly fast, but it's not as fast as a car can travel on the ground. A car on the ground can travel way faster than terminal velocity. Terminal velocity is about 120 miles an hour. Okay, a car on the ground can go faster than that. So the car on the ground was given every advantage. But you don't think about that the first time. The first time, you're just like, holy crap, they're dropping a car from a helicopter. Wow, that car on the ground is so fast. It's exactly what Lexus wants you to think. People bought this car in droves because of this ad. Okay? It was highly effective because nobody thought about it.
How did the Lexus stay like flat? Why didn't it nosedive?
They weighted it.
Oh.
Yeah, they actually put weight in the trunk to offset the weight of the engine so that it would fall flat. Yeah. Okay. Now, Mythbusters actually busted this myth. Okay. They actually did it out in a dry lake bed in like Nevada or Arizona or something like that. Okay. And the first half of the episode was them figuring out how to make a car fall like that. Because every time they dropped a car, even from a small height, it nosed down right away because all the weight was in front. So they ended up having to put a bunch of weight in the back. Okay? Then it would fall reasonably flat. But you gotta remember, the Earth's atmosphere is not uniform. There's air currents, all kinds of things like that. You can get the car, as it's falling, starting to move and rock and things like that. So what Mythbusters found, actually, was that the car falling wins. And it's close, but the car that was falling actually wins. Okay? But they didn't have the car going quite as fast, but like it was still like fairly fair, and quite a bit closer. Like that ad there, it was a little bit of camera trickery. You don't want to drop a car from a helicopter to an X. What are your chances of hitting that? From 4,000 feet? Next to zero. Yeah, you got crosswinds, things like that. So the whole thing was filmed like separately, and they dropped a car from about 20 feet and filmed that, and then put the other car, superimposed it on top, so it looked really cool. Okay, but the Mythbusters actually ran the whole thing. Okay, so if we kind of look at this, okay, we got the same distance that it's falling here, right? We know that, what's the initial velocity of the car that's falling? 0. Okay, and we know that it's going to accelerate at 9.81 meters per second squared, okay, and that it's going to fall 4,000 feet. Well, let's get 4,000 feet in meters here. I don't even know what that'll be. Google knows. $1,219. Okay. We don't know the time, right? Now we know on the ground, okay, the car is traveling at a constant velocity of 105 miles an hour. $168.981. Okay, for the same distance, 1,219.2 meters. Okay, so if we calculate how much time it takes for each of these, okay, which one should be faster? Well, let's figure it out. Okay. Oh, sorry, I'm trying to find the time, sorry. So D divided by 1/2 of A square rooted to get T. 1,219, right? Okay, so it should take that falling car 15.77 seconds. Okay, car on the ground. Okay, so 1,219.2 divided by 168.981. It's a lot faster on the ground, isn't it? Okay, every advantage is given to the car on the ground in that situation. Would you agree? All right. Now, if that's the case, why did the car that was falling win?
It had terminal velocity, the one on the ground is only traveling 105.
Yeah, and its terminal velocity was probably faster.
Yeah.
Okay, but even still, it had to start from rest. The car on the ground didn't. Okay, that's a significant advantage given to the car on the ground. Here's the other thing that this didn't take into account. Okay, this should actually be even longer because that's saying it actually accelerated all the way to the ground, and it didn't. Okay, so the only reason I can think of that the car on the ground lost is because it wasn't actually going 105 miles an hour. What were they driving on? Dirt. Yeah, it was a dry lake bed. Is it possible that the tires could be spinning? Highly possible. Okay, highly possible the tires could have been spinning. Okay, but yeah, the car is faster than gravity. Sure. Now they both started from rest. Does the car on the ground have any chance? Not a chance. Okay? And that's what everybody assumes in that ad, right? They don't realize that whole part about the car on the ground is already moving. In fact, it's already moving significantly. Now, they can't be accused of false advertising because they do actually show that that car on the ground was moving, okay? But it's not what people remember about the ad. Okay? This is where, if you have a knowledge of physics, you can pick apart the things that advertisers want to fool you with. Okay? Car on the ground should win that most of the time. Okay? It really should, especially if it doesn't have to start from rest. Okay? If it has to start from rest, it has no chance. Okay? No car accelerates faster than gravity along the ground. Okay? That's just not possible. Okay. Now, if you are trying to hit a target, this is what we were talking about before with the archer. Okay? You have to correct for drop. Right? So if we're looking at, a sniper who's hitting a shot that's over 3.5 kilometers, like that one we were talking about earlier in the unit, okay? Is that a long flight time? Absolutely. Guys, if a projectile is in flight for 1 second, it falls 4.9 meters in 1 second. Okay? Is that a long way? It is. So if you're, shooting a gun that shoots a projectile at, let's say, 1,000 meters per second, okay, and you're shooting at a target that's 3.8 kilometers away, that means that the bullet's in the air for 3.8 seconds. Okay? In the first second, that object is going to fall 4.9 meters. The next second is going to fall further than that because it's accelerating. And the next second further than that. Okay? And the person who's pulling the trigger has to account for that when they are trying to hit that target. When they're aiming, they have to account for all of that. Okay? They have to account for crosswind. They have to account for the Coriolis effect. As the bullet flies through the air, the earth will spin under it. Okay? All of that stuff has to be taken into account. It's a lot to think about. Okay? Projectiles, okay, are not kind of the easy thing that we kind of think they are. They are over short distances, like shooting archery, okay, or throwing a football to somebody else, or a baseball to somebody else. Those are short projectiles. Okay? Even if you're, hitting a driver in golf, you're only the ball's only going to travel, 250 meters. Okay? That's still a fairly short projectile. All that stuff is fairly predictable. right? But when we start dealing with the kind of ranges that some of the projectiles we use can travel, okay, it's quite a bit more complex than that. Okay, now, movies often portray projectile motion falsely, especially modern movies, okay? Because they show, well, CG so much of the time. Okay? Now, CG modeling is getting better, so things look a bit more realistic, okay? But sometimes it just looks bad. How many people have seen a movie where a car drives off a cliff? Okay? What does it look like? Yeah, at first it looks like it's flying, right? And then it just looks like it's falling. And it looks like it's not moving forwards anymore. Is it? Or is it still doing both? It's moving horizontally and vertically the entire time. But by the end, depending on the height of the cliff, of course, but by the end, it looks like it's only moving vertically, because the vertical part becomes the dominant part of the motion. Okay? When you first drive off of a cliff, you're only moving which way? And we're clear that no one's going to try this at home. This is all theoretical exercise. Okay? When you first go off of a cliff, or you run off of the diving platform at the pool, all of your motion is horizontal, at least at time zero. Okay? But as soon as you step off, now gravity is trying to pull on you. Right? But if you were going fairly fast, at least initially, more of your velocity might be horizontal. Okay? But over time, it's going to become more and more vertical. It makes it look like by the end, all you're doing is falling. But it's only because you're traveling faster vertically than you are horizontally by the end. Okay? Objects are still traveling horizontally. It just doesn't look like it as much. Okay? Everyone kind of follow me there? So, let's say that you're flying in a bomber, and you want to be able to drop a bomb on a target, like in Top Gun. Okay, when they did all the practice runs, okay, and they had to drop the bomb on the target. Okay, a bunch of them missed because they dropped them either too early or too late. Okay, is it a pretty finicky thing to try and get that thing to fall in the right place? Because when you drop it, it's moving not just vertically, but horizontally as well. So you have to take into account your velocity at the moment you drop the bomb. Because the bomb is going to move at that velocity horizontally the entire time until it hits the ground. And it's going to accelerate vertically at the same time. Okay? It's not an easy calculation by any stretch. Okay? That's why there's one person in charge of dropping the bomb. That's their job, their one job. And is to make sure that that bomb gets released at the right time. And contrary to what it might have looked like in Top Gun, that is not a seat-of-the-pants gut reaction kind of thing like they make it look like. Okay? It is entirely computer calculated so that that thing actually hits the target. All right, so let's watch. We've got a couple of videos. There's a lot of videos over the next couple of days because there's lots of really bad movie physics. I want you to copy this example down here. So we got our rebel without a clue. Okay? We're going to drive off the cliff at 25 meters per second. The height of the cliff is 60 meters. And we want to calculate how far from the base of the cliff the cars will hit. Okay, so the key to any projectile motion problem, okay, and we're going to deal with essentially two kinds. This kind, which we call a projected horizontally question, okay, and the other kind is projected at an angle, which we'll look at tomorrow, okay. But for one that's for any projectile problem, you have two dimensions. You have the horizontal dimension and you have the vertical dimension. And what you have to remember is this: horizontally, the object travels at a constant velocity. Okay? That means that until this car hits the ground, it is traveling at a constant horizontal velocity of 25 meters per second. vertically speaking, the object is going to accelerate because of gravity. Okay? So what I want to do is separate the two parts and write down what I know vertically and what I know horizontally. What's the one thing that they will share? Think to the both questions. Those are two-dimensional motion as well. And there's one thing that both dimensions share. Time. This car is moving horizontally and vertically until it hits the ground. Therefore, it is doing both for the same amount of time. So in most projectile motion problems, the most valuable piece of information is time, because you know it applies to both parts. Okay? So, vertically speaking, I know that this object, this car, is going to fall 60 meters vertically. Okay? I also know that it's going to accelerate vertically at 9.81 meters per second squared. What else do I know about it vertically? How fast is the car going vertically when it drives off the cliff? 0. It's moving horizontally when it goes off the cliff. Okay? But the instant it drives off the cliff, it isn't moving vertically yet because it drove horizontally off the cliff. So for any projected horizontally problem, the initial vertical velocity is 0. If I throw something at an angle up in the air, its initial vertical velocity is going to be some value up. If I throw it at an angle down, it's going to have some vertical velocity down. Okay? But in this case, it went off horizontally. It wasn't moving vertically. Could I use that information to get time? Probably. Okay? So we're going to call this our vertical information. Okay? Horizontally, right now, I only know one thing. That. Now, we said we want to calculate how far from the base of the cliff they're going to hit the ground. Is that a horizontal value or a vertical value? It's a horizontal value. It's the horizontal displacement. That's what this question's wanting me to find. Okay? Because that would be that number. Okay? How far it travels horizontally. Okay, so if I want to get the horizontal displacement, and I know I'm traveling at a constant velocity, I need the time. Right now I don't have it. But I can calculate it with my vertical information. This formula is going to come up all the time. Okay? Came up in our acceleration lab. It's going to be important in projectile motion all the time. Okay? It's an extremely versatile formula. All right, since VI is 0, that whole first part is 0. Right? I'm trying to calculate the time, so I'm going to divide both sides by half of A, and then I'm going to square root. Okay, I'm just typing in half of 9.81. I'm taking a bit of a shortcut here. If you're wondering what that number is, I just did the half of 9.81 in my head. Okay, so the cars after they drove off the cliff are falling and traveling horizontally for 3.5 seconds. Is that a long time? It's a long screen. Okay, but it's a long time to fall. All right, so I can bring that time over here. We said time is the one thing that both the horizontal and vertical parts share. Okay, you're moving horizontally until you hit the ground. You're moving vertically until you hit the ground. So if I want to find how far from the base of the cliff they're going to hit, I take V times D. Right, so it's going to be like, what, 80 something? Right, 87 meters. That's quite a ways out, actually. Okay, so here's what you need to know about basically all projectile motion. It has a vertical and a horizontal component. Okay, those are both different kinds of motion. Horizontally, it's constant velocity. Vertically, it's accelerated. And they always share time. Okay, the time is always going to be the same for both parts. Okay, everyone with me there? Yeah. So is there a number of ways I can manipulate a question like that? Like on that one, I asked you to solve for how far from the base of the cliff they hit. Could I give you a similar question and say, here's how far from the base of the cliff they hit, how high is the cliff? Yeah, but it'd be the same steps in a different order. I'd have to find time. Then I go back to the vertical part with the time and calculate the vertical distance. That would be the height of the cliff. Okay? Right? Or I could say, here's how far from the base of the cliff they hit, here's how high the cliff is, what speed did they drive off at? Right? There's only a certain number of things I could ask you to calculate in a question like this. Okay? But the steps are always going to be the same. Okay? It's just the different order in which you're going to do them. Right, the bomb. I got to do the bomb. What time is it? We got time. Okay, so the plane is moving at 200 meters per second. The bomb is going to travel 1,800 meters horizontally. What altitude do they drop the bomb from? Okay, we're looking for the altitude the bomb is dropped from. Give you a couple minutes and then I'll write a couple more things on the board and then I'll give you a little bit more time after that. Okay, let's just look at what our givens are for this question just to kind of help you get started. Okay, so what we always want to do is break this up into our vertical and horizontal components. Okay, on this question, I know more horizontally than I do vertically. Okay, what two pieces of information do I know horizontally? I know the distance it traveled, or the displacement, 1,800 meters. What else do I know horizontally? If the plane was moving at 200 meters per second, how fast is the bomb going? 200 meters per second. That's also a piece of horizontal information. Okay? Vertically speaking, I know the acceleration, 9.81 meters per second squared down, and I know one other piece of vertical information. VI. What's VI?
200 meters per second.
That's the horizontal. So the plane's traveling along, it's moving horizontally. So is the bomb. What's the initial vertical velocity? 0. Bomb isn't moving vertically when it's released. Okay? The instant after it's released it is, but it isn't moving horizontally at time, or sorry, vertically at time 0. Okay? What they want is the altitude it was dropped from, which would be the vertical displacement of the bomb. Okay. See if you can solve it. Remember, the most important piece of information is time. I'd look for that. Okay, let's have a look at this one. So, can I find, which part can I find my time with? I can find my time here? How?
Like, use 9, or sorry, the horizontal.
With the horizontal, yeah, okay? Because horizontally, I know that it's traveling at a constant velocity, which means I can use this formula. Okay, if it's traveling at a constant velocity. So I just have to solve for time. Time is going to equal d over v, so 1,800 meters divided by 200 meters per second, okay, should give me 9 seconds, yes? Okay, so now I know that the bomb is falling for 9 seconds. Now I have an additional piece of vertical information. Can I find the altitude it was dropped from? In other words, its vertical displacement. Okay, I just solved for time. VI is 0. I know the acceleration is 9.81. Pretty sure I can solve for D. Okay, are you seeing why we did this last in the unit? And we haven't even gotten to the angled ones where we have to find X and Y components. Okay, so that's going to bring in the vertical part, or the vector part. All right, so we got 1/2 times 9.81, which I'm making positive simply because it doesn't change direction. It only moves down, so I'm making down positive. Okay, times 9 squared. All right, so 0.5 times 9.81 times 81. All right, so they were just under 400 meters above ground level. In fact, if we do this to two significant figures, it would be 4.0 times 10 to the 2 meters would be the altitude it was dropped from. I would say that's a little close to the ground, dropping over a nuclear weapon. Okay, now, something we didn't see there that's kind of important. If I'm that bomber, and I drop that bomb, and I keep flying straight, where am I going to be when it goes off? Right over top of it. Because me and the bomb are both moving at 200 meters per second horizontally. So if you ever become a bomber pilot, it is not a good idea to keep flying in the same direction after you drop the bomb, or you're going to be right over top of it when it goes off.
Did they also detonate bombs above ground? Yeah, especially.
Yes, nuclear weapons are typically detonated above the ground. Yeah, because they cause more damage that way. Yeah. Okay, guys, no quiz tomorrow. Okay? You do have a fair number of things coming due in the next little while, so make good use of your time, would be my advice. Okay?